In this lecture video, we're going to look at estimation in the context of the completely randomized design. Now, in particular, we're going to be looking at point and confidence interval estimation for treatment means, differences between treatment means, and linear combinations of treatment means. Now, let's look at estimating treatment means first. Recall that the means model version of the statistical model for the completely randomized design is given by the model here on this slide, y sub ij equal to mu sub I plus epsilon sub ij, where mu sub I is the mean, the population mean under treatment I. In this expression, I goes from 1 up to t, where t is the number of treatments, and then for each I, j, which is the observation index, goes from 1 up to r sub I, where r sub I is the number of observations or the sample size for under treatment I. Now consider the mean response in the sample receiving treatment I. In other words, the sample mean for the sample that has received treatment I. Now you'll recall that we denote that sample mean by y bar sub I, and it turns out, based on this expression for the statistical model, that the sample mean for the treatment for the sample receiving treatment I, y bar sub I, is equal to mu sub I plus epsilon bar sub I. Now, the term epsilon bar sub I in this expression is the mean of the error terms for the observations in that sample. In other words, epsilon bar sub I is equal to 1 over the sample size of the sample receiving treatment I times the sum of those error terms. So the observed sample mean, y bar sub I, is the sum of the unobserved and unknown mean response under treatment I, again mu sub I, and the unobserved average of the error terms associated with the observations in that sample. Now, the goal is to estimate mu sub I, which is again the mean response under treatment I, and to do that for each of the treatments. Now, from this expression for y bar sub I, it can be shown that the expected value of y bar sub I, in other words, the mean of the sampling distribution of y bar sub I, is equal to mu sub I. Now, this implies that the sample mean, y bar sub I, is an unbiased estimator of the treatment mean, mu sub I. Now, because of this, we're going to be using the sample mean of the ith sample, y bar sub I, as an estimator of mu sub I. And we're going to express this notationally by using, again, what we call hat notation. All right, and so the goal is to estimate mu sub I. And so we're going to denote its estimator by putting a hat on top of mu sub I. So we have mu hat sub I, and that estimator of mu sub I is the mean of the sample that received treatment I. And that obviously then applies for each of the treatments, I going from 1 up to t. Now, in order to go beyond point estimation, we have to understand the variability associated with that point estimate. And so now we're going to look at the variance and the standard deviation of this estimator of the treatment mean. Now, the true variance and the true standard deviation of the sampling distribution of mu hat sub I, the estimator of mu sub I, are given here in the middle of the slide. So the variance of mu hat sub I is equal to sigma squared over r sub I, where again sigma squared is the variance of the error term in the model. Now notice that we've got two different ways that we are going to be representing the variance of the sampling distribution of mu hat sub I. We will denote it this way, var of mu hat sub I, but we will also denote it this way, sigma squared with mu hat sub I in the subscript. All right, and so again, this is read the variance of mu hat sub I. And again, it's equal to the variance of the error terms in the model divided by the sample size for the ith sample. Now, once we have this expression for the variance, the standard deviation is just the square root of that variance. And so the standard deviation of mu hat sub I, which we will denote a couple different ways. We'll denote it this way, SD for standard deviation of mu hat sub I. We'll also denote it this way, sigma sub mu hat sub I. All right, so there are no surprises there. We're should be fairly used to that kind of notation at this point. And again, the standard deviation of the sampling distribution of mu hat sub I is just the square root of the variance, and so we could write it in either of these two ways. The square root of sigma squared over r sub I, or as sigma over the square root of r sub I. Now, these are the expressions for the variance and the standard deviation of the sampling distribution of mu hat sub I, but we're not able to calculate these because they depend on the unknown variance of the error terms. They depend on sigma squared, and that is not known. And so we're not able to calculate these quantities, and so we'll have to estimate them. And so with that in mind, we look now at the estimated variance and estimated standard deviation of the estimator of a treatment mean. So recall in our discussions about how to do the ANOVA, the analysis of variance, under the completely randomized design, recall that an unbiased estimator of the variance of the model error terms is provided by the mean squared error, the MSE, in the ANOVA table. All right, and so we denote that estimate of sigma squared by sigma hat squared, and the estimator of the error variance that we obtain from the ANOVA table is the mean squared error in that ANOVA table. So once we have this estimator of the variance of the error terms, we can then plug that estimate back into the expressions for the variance and the standard deviation of the sampling distribution of mu hat sub I to obtain the estimated variance and the estimated standard deviation for mu hat sub I. And so we will denote the estimated variance in a couple ways. Notice that I put a little hat here on top of the variance. All right, so the estimated variance of mu hat sub I. And I'm also going to denote this this way. I put a hat on the sigma squared sub mu hat sub I. All right, and so there are a couple different ways that we're going to denote that. And that is, this estimate is given by or equal to sigma hat squared over the size of the ith sample, or in other words, it's MSE, the mean squared error from the ANOVA table, divided by the size of the sample receiving treatment I. The estimated standard deviation of the sampling distribution of mu hat sub I is denoted this way. I've got a hat on SD here. We'll also denote it this way. I've got a hat on the sigma, so sigma hat sub mu hat sub I, and that is the square root of the estimated variance. All right, so the square root of sigma hat squared over r sub I, or in other words, the square root of the MSE from the ANOVA table divided by r sub I. Once we have the estimated variance and the estimated standard deviation of the sampling distribution of mu hat sub I, we can then use those along with the point estimate to come up with a confidence interval estimate for a treatment mean. In particular, a 1 minus alpha times 100% confidence interval estimate of the ith treatment mean, mu sub I, is given by this formulation here. So mu hat sub I, the point estimate, minus plus the margin of error for the interval, the margin of error being equal to the product of the interval coefficient, which comes from the t-distribution, and the estimated standard deviation of mu hat sub I. And note that we will also call the estimated standard deviation of the sampling distribution of mu hat sub I, we'll also call that the standard error, the estimated standard error of mu hat sub I. So we'll be using that terminology as well. Okay, so this is the margin of error, again, for the interval, Again, it's the product of the interval coefficient times the estimated standard error of mu hat sub I. Okay, and we can then rewrite that in any of these other two ways. Now, the interval coefficient, again, comes from the student's t-distribution, and in particular, the interval coefficient is the upper alpha over 2 percentage point of the t-distribution. And you'll recall that in order to use the t-distribution, we have to know how many degrees of freedom we have. And the number of degrees of freedom associated with this is equal to r dot minus t. You'll recall that r dot is the notation for the total sample size, the sum of the sample sizes for all the different samples. All right. This is the number of degrees of freedom associated with the error term with the mean squared error in the ANOVA table. So if you go back and look at that ANOVA table for the completely randomized design, the number of degrees of freedom associated with the variability associated with the within samples, or what we call the error in the model, is equal to this quantity here. So it's the number of degrees of freedom associated with our estimate of sigma squared, and so that is the number of degrees of freedom associated with this t-value. Next, we'll look at point estimation of a difference between treatment means. So based on what we've just learned about how to estimate a particular treatment mean, we can now very easily come up with a way to estimate a difference between treatment means. In particular, an unbiased estimator of the difference between treatment mean I and treatment mean I prime is given by the following. So I'm going to denote the estimate of mu sub I minus mu sub I prime by putting a big hat over that, okay? And so our estimate of mu sub I minus mu sub I prime is equal to the difference between the individual point estimates of mu sub I and mu sub I prime. So in other words, mu hat sub I minus mu hat sub I prime. So that is our unbiased estimator for the difference between mean I and treatment mean I prime, mu sub I minus mu sub I prime. This is the estimator for that. Now, in order to construct confidence intervals for the difference between two treatment means, we need to understand and have expressions for the variance and the standard deviation of the estimator of the difference between those treatment means. And so that's what we have on this slide. The variance of the sampling distribution of the estimator of mu sub I minus mu sub I prime is denoted in a couple ways. Again, var, variance of the estimate of mu sub I minus mu sub I prime. We will also denote it using this notation, right? Sigma squared with the estimator down in the subscript. So mu sub I minus mu sub I prime with a hat over all of that. And so that's a notation. They represent the variance of this estimator, and that variance is equal to sigma squared times the quantity 1 over r sub I plus 1 over r sub I prime. And this follows from the fact that the samples are independent of each other. Now, once we have this variance, the standard deviation for this estimator is obtained by taking the square root of the variance. And so again, the standard deviation for the estimator of mu sub I minus mu sub I prime, also denoted by sigma sub with a hat over mu sub I minus mu sub I prime, that's equal to the square root of this variance. Now, again, because these expressions depend on the unknown value of the variance of the error terms in the model, we're not able to construct or calculate these quantities exactly, and so they have to be estimated from the data. Now, before we do that, though, let me just point out that if there is equal replication under treatments I and I prime, In other words, if r sub I is equal to r sub I prime, then the formulas for the variance and the standard deviation of the sampling distribution of the point estimate of mu sub I minus mu sub I prime simplify, and they're equal to the following. So the variance of the estimator of mu sub I minus mu sub I prime is 2 times the error variance divided by the common sample size for those two samples. And the standard deviation would then be the square root of that. So you can use, if you have equal replication, you can use this simplification, or you could obviously compute that as well, or use that expression as well. But if the sample sizes are different, you have to use this version. You cannot use the simplified version. But again, whichever formulation applies here, we're not able to calculate these quantities exactly because we don't know the variance of the error terms. We don't know sigma squared. All right, so but we can use the same approach that we used in coming up with the estimated variance and estimated standard deviation for treatment mean estimators by replacing the unknown sigma squared by its estimator, or the unknown variance sigma squared by its estimator sigma hat squared. And so estimators of the variance and the standard deviation of the sampling distribution of mu sub I minus mu sub I prime hat are obtained by replacing in each of these formulas the unknown error variance sigma squared by its estimate sigma hat squared, which again is the mean squared error from the completely randomized design ANOVA table. And so we get these expressions for the estimated variance of this point estimator and the estimated standard deviation of that estimator. And also notice that we are distinguishing between the actual variance and the estimated variance by putting a hat on the estimated variance, and likewise differentiating between, notationally differentiating between the true standard deviation of this estimator and its estimate, again by putting a hat on the notation here. And again, if there is equal replication under treatments I and I prime, then these estimators simplify somewhat. All right, so the estimated variance of the point estimate of the difference between the treatment means would be 2 times sigma hat squared divided by r sub I, the common sample size, or in other words, 2 times the mean squared error divided by r sub I, and then the estimated standard deviation would simplify as well, just being the square root of that estimated variance. Once we have that, then we are able to construct a 1 minus alpha times 100% confidence interval estimate of the difference between the treatment mean I and treatment mean I prime. That confidence interval given by the point estimate minus plus the margin of error. So again, we start off with a point estimate of mu sub I minus mu sub I prime. And then from that point estimate, we go a distance to the left and to the right to get the endpoints of the interval. And that distance is the margin of error, which is the product of the interval coefficient that comes from the t-distribution and the estimated standard error of mu sub I minus mu sub I prime hat. Okay, and so that is given by the point estimate being the difference between the individual treatment mean point estimates, so mu hat sub I minus mu hat sub I prime, minus plus, and then the product of our interval coefficient from the t-distribution and the estimated standard error, which in this case is the square root of MSE times 1 over r sub I plus 1 over r sub I prime. And again, if we have equal replication under these two treatments, then this would just be, under the square root sign, that would just be 2 times MSE over the common sample size. Again, the interval coefficient, the t-value is the upper alpha over 2 percentage point of the t-distribution with degrees of freedom that are equal to the number of error degrees of freedom in the ANOVA table. All right, now we're going to look at estimation of a linear combination of treatment means. And this is a generalization of what we've looked at in the last bit of material here. So more generally, suppose that we are interested in making inferences about a linear combination of the treatment means. This linear combination given by this expression here. So it's the sum, I going from 1 up to t, the number of treatments. The terms in the sum being a sub I times mu sub I. All right, so this is a linear combination of the treatment means. Recall that if the sum of the coefficients, the sum of the a's, is equal to 0, then the linear combination is a contrast and therefore represents some sort of comparison between the means. Now, an unbiased estimator of the linear combination of the treatment means is given by this expression here. So notice that I've got a hat over this notation for the linear combination itself. All right, that estimate, the estimator is given by the same linear combination, but the linear combination of the treatment mean point estimates. Right, and so notice that we've got a hat on the mu sub i's here. So we're dealing with, we're constructing this linear combination of the individual sample means. Okay, so that is the point estimate for that linear combination. But again, in order to go beyond that and construct a confidence interval, either a two-sided confidence interval or there may be some situations where we just want either a lower confidence limit alone or an upper confidence limit alone. In order to do that, we need to first understand the variability associated with that point estimate of the linear combination. And so it can be shown that the true variance of the sampling distribution of this estimator of the linear combination is given by this expression here. So notice here, okay, so let's look at this notation. I have the variance of the estimator of the linear combination. We can also denote that as sigma squared with the estimated linear combination in the denominator, or not the denominator, the subscript. Apologize for that. All right, and so we'll denote this variance in each of these two ways. And this variance, the actual expression for the variance is given by this expression here. It's the variance of the model error terms, sigma squared, times the sum, a sub I squared over r sub I. So this is the true variance of this estimate of the linear combination. But again, because it depends on the unknown error variance, this variance is unknown and therefore must be estimated. The true standard deviation of the sampling distribution of this estimator of the linear combination is obtained by just taking the square root of the variance. All right, so that's what we've done here on the far right hand side. And we are going to denote that in a couple different ways. SD, standard deviation of that estimate of the linear combination, or we'll also denote it as sigma sub, and then the point estimate in the subscript. Now again, we're not able to calculate this exactly because we don't know the unknown error variance, and so we would have to estimate this using the data. And again, the way we do that is by plugging in the estimate of sigma squared that we obtain from the ANOVA table. So the estimated variance of this estimate of the linear combination is equal to sigma hat squared, which is MSE, times the sum, I going from 1 up to t, of a sub I squared over r. And then once we have that, we can come up with the estimated standard deviation for this estimate of the linear combination. And again, it's just the square root of the estimated variance. And note also, as usual, we are putting hats on our estimates for the standard deviation or standard error of this linear combination of the linear combination. Once we have the estimated standard error, we can construct a confidence interval for the actual linear combination. So a 1 minus alpha times 100% confidence interval estimate of the linear combination is given by the point estimate minus plus the margin of error. Again, the margin of error is equal to the product of the interval coefficient from the t-distribution and the estimated standard error of the estimate of the point estimate of the linear combination itself. All right, and so we have expressions for that on the previous slide. And so we also have the expression for this point estimate. It's the linear combination of the point estimates of the treatment means. All right, so again, we have that as our starting point, and then we go a distance to the left and to the right equal to the margin of error, which is equal to this expression here, this product. Okay, and again, the number of degrees of freedom associated with the interval coefficient from the t-distribution is equal to the number of error degrees of freedom associated, or the number of error degrees of freedom from the ANOVA table, which is again, the number of degrees of freedom associated with our estimate of sigma squared. And so these are the formulas that we use to compute point and confidence interval estimates for treatment means, for differences between treatment means, and in general, for linear combinations of treatment means. The results for the estimates of treatment means and differences between treatment means are special cases of the more general linear combinations of treatment means. And so, and you can also come up with really any kind of estimate for that is typically of interest in the context of an ANOVA in comparing treatment means. So you're not restricted to just looking at differences between treatment means. You can use these formulas to come up with estimates, point and confidence interval estimates for any linear combination of the treatment means that is relevant and makes sense in the context of a particular experiment.